In section 9.3, we're going to talk about two means and independent samples. So let's start by talking about two independent samples. So the data in a randomized comparative experiment consists of a sample of n observations, which we'll call each observation an x sub I, from population A and a sample mean of x bar, and a sample standard deviation of s sub x. Together with a sample of m observations, which we'll call y sub I, from population B with a sample mean of y bar and a sample standard deviation of s sub y. The point estimate of the difference in population means, or mu A minus mu B, because we're talking means again, we're going to be estimating each one with x bar. So we'll have the point estimate for the difference in population means, which parameter would be mu A minus mu B. The point estimate, or our sample statistic, will be x bar minus y bar. Since we know that the variance of x bar is sigma squared of A, right, population A, over n, and the variance of y bar is sigma B squared, because that's population B, divided by m. When we know the population variances, we can then say the standard deviation of the sampling distribution, which we call the standard error, of x bar minus y bar is given as our standard error here, SE of x bar minus y bar, then is equal to the square root of sigma x squared over n plus sigma y squared over n, or sigma from population A squared over n, which is the size of population A, well, not population, sorry, sample A, plus a sigma y is the same as sigma from population B squared over m, the size of our sample from population B. And if we need to estimate the population standard deviation, then instead with just the sample standard deviations, then for those ones, we're just going to use s sub x and s sub y. And when we do that, our standard error of x bar minus y bar then is going to be the square root of s sub x, standard error of our sample in terms of x, of population A, over the size squared over the size of that sample, which is n, and then we'll do the same thing by adding up this sample standard deviation of population B, which we'll call s sub y squared, over the size of our sample from population B, which is size m. And just like we had before with single means, we're going to use a two-sample z-test if we know the population variances, and we'll do a two-sample t-test if we only know the sample standard deviations. So just like in previous sections, if we know population standard deviations or variances, we use z because we can assume they're normal. And if we don't, that little extra variation thrown in by estimating the population standard deviation with a sample standard deviation means we have to use a t-distribution. So one more time, if sigma and for each one, so if sigma x or A and sigma y or for B are known, we'll use a two-sample z test. And if we only know the sampled standard deviations for each of our samples, right, those are the only ones we know, then we will use a two-sample t-test. So again, this goes back to exactly what we talked about previously. If you know sigma, you use z. If you only know s, you use t. So how do we end up actually running these tests when we're talking about two separate samples? We're not going to pair the data because this is not a before and after. So how do we manage this now that we have two separate samples from possibly two different populations, 1A, 1B? Well, then we're going to consider the two-sided problems of the form then, where our null hypothesis is that the difference is equal to a value mu naught. Oftentimes this is going to be 0, but for now, we're just going to call it mu naught like we did before when we're only looking at one mean, or we're looking at our paired data where we analyzed it like it was one mean. So if our null hypothesis is that mu A minus mu B is equal to mu naught, we're going to be looking at the two-sided test where mu A, for our alternative, mu A minus mu B is not equal to mu naught. So let's take a look at our two-sample t-test first, because oftentimes that's what we're going to have. We will rarely have the information about a standard deviation from a population. Most of the time, we're going to have sample standard deviations. So let's look at and see what that means. So if we consider a sample of size n from population A with a sample mean of x bar and a sample standard deviation of s sub x, and a sample of size m from population B with a sample mean of y bar and a sample standard deviation of s sub y, then we know a two-sided 1 minus alpha level confidence interval for mu A minus mu B is given as x bar minus y bar minus t sub alpha over 2 nu times the standard error, which is the square root of the variances squared over their respective sample sizes. And here I'll just highlight the whole thing. So that is our confidence interval for a two-sided t-test. So where the degrees of freedom, and this is where things get a lot different. So far, it's been pretty much the same thing as what we did with just one or with paired data. But now our degrees of freedom get very, very intricate here. They get very complicated because now we have to include two different samples from two different populations. So we can't just do n minus 1 and m minus 1. Some of that will show up here in this formula, but not always in the way that we maybe think they will. So let's see, what is our new definition here, our new formula for degrees of freedom? And it is this big, ugly fraction in the middle here. So nu is now, in the numerator, we're going to have standard deviation of x squared divided by n plus a standard deviation of y squared, or the variance of y, over m. And then we're going to add them up just like we do under the square root for our standard error. But instead, we're going to square it. So we have that squared, and that entire thing is our numerator. Our denominator is where things get even trickier. We then have s to the fourth in terms of x. So the standard deviation in terms of x to the fourth power divided by n squared times n minus 1. Remember, n is the size of our sample from population A. And then we're going to add to that the same thing, but now in terms of y. So we'll have the standard deviation in terms of y to the fourth power divided by m squared times m minus 1, where remember m is the size of our sample from population B. Yes, you're going to have to do this by hand. You are going to have to calculate some degrees of freedom by hand. This is where using our desmos.com/scientific becomes so incredibly helpful, because you can visualize every single fraction. It's very, very nice. You could also use alpha y equals on the TI-84, but this is so much easier to see. So my suggestion is for these ones, and I'll even put a little note here, I'm going to suggest that you use, so I suggest using Desmos. I suggest using Desmos. By the way, this is also on our formula sheet. Okay, so you don't have to memorize this. You don't have to put it on your card. It is on the formula sheet. We haven't really looked at what's on there yet for Unit 3, and there's a lot of stuff on there. There's a whole lot of stuff on there for Unit 3. In fact, I believe it's the entirety of the backside of our formula sheet is all for Unit 3. So you'll have this on there. So if we know now how to find our degrees of freedom, complicated as it may seem, can we use it to help us in terms of finding our test statistic t and running our hypothesis test, finding our p-value, all of those things? And the answer is yes. So the appropriate t statistic, or our test statistic for our null hypothesis, where mu a minus mu b is equal to mu naught, is then given by another one of these sort of large formulas here. And this one in particular says that our t, our test statistic t, can be given by x bar minus y bar minus mu naught, and then we'll divide it by the standard error. So this shouldn't feel all that different from what we've done in past sections. Mean minus the hypothesized value for mean divided by the standard error, which is s squared over n. Take the square root. Sounds pretty similar. So it is, it's just that now when we do s squared over n, we also have to add to it s squared over m. And remember, those s's are related to their samples. And then we take the square root of that. So we're just putting it all together. And how does this now relate to our two-sided t-test? Well, in order to do our p-value, we have to remember this is a two-sided test. So our two-sided p-value is calculated as 2 times the probability that x is greater than the absolute value of t, where the random variable x has a t-distribution with new degrees of freedom, and one-sided p-values are where x is greater than t, or the probability that x is less than t. So none of that should feel terribly new because it's kind of what we've already been doing. How does this change now if we only need to worry about z? Well, the degrees of freedom goes out the window. We don't have to worry about it because we're dealing with a normal distribution. So if we are considering the same setup we have n samples from population A with a sample mean of x bar, and we assume that we have a population standard deviation this time of sigma sub x. And then we repeat this again then with sample size m from population B with sample mean y bar and an assumed population standard deviation of sigma y, then we can build our two-sided 1 minus alpha level confidence interval for mu a minus mu b. And what does that one look like? Well, that one is right here. And that one says that we've got x bar minus y bar. My pens are being fun. They don't want to change colors. I guess we're going to get green. We have x bar minus y bar. And then we subtract from that our z sub alpha over 2, because again, two-sided. Z sub alpha over 2, and then the same standard error, except that now we have sigma in there. And our appropriate test statistic then, which would be our z statistic, is then given by, in a very analogous way, z is x bar minus y bar minus mu naught divided by the standard error, now with sigmas instead of s's. And a two-sided p-value is calculated as 2 times phi of the negative absolute value of z, and a one-sided p-value then would be 1 minus phi of z and phi of z. So again, all we're really doing at this point is just converting all of the work that we did for a single mean or even paired data means over to now two means and a difference of two means. So let's see what this looks like in practice. We're going to do, I think it's 3 problems together. Yeah, 1, 2, and 3. We're going to do 3 problems together and work through these, and then you guys can work on the assignment that I passed out after the last exam for you to do while I'm gone. So for example, 9.3.1, we have a data table here that shows the scores of 15 patients who underwent the standard treatment for acrophobia, an intense fear of heights, and the scores of 15 different patients who underwent a new treatment using VR, virtual reality. Higher scores correspond to greater improvements in the patient's condition. The sample data is also given with their respective box plots. Is the difference in means between the old and new treatments statistically significant? So we have our population A over here with a size of 15. And we have population B over here with a size of also 15. So A and B. And if we look at our standard treatment, we can see our first box plot up here. And it definitely seems to have a lot more variability than our new box plot, because look how long these whiskers are. The mean looks like, or the median, sorry, looks like it's just slightly lower than that of the new treatment. So we'll see how this goes. Maybe with less variability and a median and a Q1 and a Q3 that are higher, maybe we'll see a difference. Maybe we'll see that B maybe does work a little bit better. So let's talk about what we were given. So we know the sample size for population A, well, sample A from population A is size n. We know that it has a sample mean x bar of 47.47 and it has a sample standard deviation s sub x of 11.4. And then we also have our m over here, our sample size for the new treatment or population B, our sample from population B. It has a y bar and it has a sample standard deviation s sub y. So what does that mean? Well, first of all, let's define what our hypothesis test means. Our hypothesis test says, well, I'm trying to say what is my null, what is my alternative. What we want to see is in the alternative, is B actually better than A? Right? Is it better? So is mu sub A less than mu sub B? Which means that our null has to be that mu sub A has to be greater than or equal to mu sub B. And remember, these are the same as saying, I'll put them over here in parentheses, that mu A minus mu B is greater than or equal to 0, and this would be the same as mu A minus mu B is less than 0. And you can get that just by subtracting mu B over to the left-hand side. And when we do that, that makes our mu naught equal to 0. So when you're only looking to see, is there a difference? Then that usually means that our mu naught is 0. Oftentimes, our mu naught will be 0. So in this case, we know that mu naught equals 0. So what else do we need to know? We need to know our sample statistic. So let's get that. So our sample statistic here, so our sample statistic is going to be x bar minus y bar because we have mu A minus mu B, so we keep them in the same order, x bar minus y bar, or 47.47 minus 51.20. Yes, it is going to be negative, so x bar minus y bar then is a negative 3.73. And this makes sense because our alternative is that mu A is less than mu B, which means it should be a negative number if our data is showing us. So we would know that something was wrong, that something had gone awry, if instead of when we theorized our alternative, if we said mu A was less than mu B, but when we did x bar A minus x bar B, we got a positive, then why are we supposing that or theorizing that maybe it's negative if we really get a positive for our sample statistic? So this is when you have to make sure everything is matching, right? All of our signs are jiving here. So our sample statistic is x bar minus y bar. It should match what we have in our alternative hypothesis, which is that the difference of A minus B is less than 0. We got x bar minus y bar, which is A minus B, and it's negative. So that does hold true. So far, we're on the right track. Now we have to go through and calculate our degrees of freedom, your favorite part. So let's see if we can manage to figure out how to find these degrees of freedom with this crazy formula. So we need to get our degrees of freedom. Degrees of freedom. So we have nu is equal to, well, it's going to be a doozy. Let's see if I can write it all out for you without making a huge mess here. Let's do 11.40 squared over 15 plus our 10.09 squared over our sample size of 15. And this is all squared. And our denominator will have our 11.40, but instead of squared, now it's to the fourth, and it is divided by n squared, which is 15 squared, times n minus 1, which is 15 minus 1. And we'll add to this the same thing, but in y, so 10.9 squared, or sorry, to the fourth, over 15 squared times 15 minus 1. And when we calculate all of this together, we end up at 27.59. And the one really interesting thing to note about degrees of freedom is we always round it down. So we're going to round down to 27. And this is going to feel uncomfortable because you have 27.59. And your instinct is to round up to 28. But remember what happens when we talk about our degrees of freedom. The higher the number of degrees of freedom, the closer it is to truly being a normal distribution. And so we can't let a fraction of a degree of freedom move us closer to that normal. We go with our worst case scenario and assume it has the worst variance of the two. So, or that variance is playing a bigger role in this case. So we'll round down every time. So we're going to round down to 27. So our degrees of freedom now is 27. So what next? Well, just like before, now we're going to find our test statistic. And since we're doing a t distribution, our test statistic is a t. So we need to find our test statistic t. So here's our test statistic. Let's find t. And t is going to equal x bar minus y bar minus mu naught over the square root of s sub x squared over n plus s sub y squared over m. So in this case, we got it was a negative 3.73, right? Minus, well, mu naught is just 0. And we're going to divide it by the square root of, let's see, s sub x is 11.4. So 11.40 squared over 15 plus our y was 10.09. 10.09 squared over 15. And when we add all of this up, we get a test statistic t of a negative 0.949. And now we need to test this p-value. So how do we do that? The same way we always have. We have to go in and do our t.dist, and we have to find our p-value. So let's do that. Let's do our p-value. Okay, so here our p-value. So in order to find our p-value, we want to find the probability. So all right, our p-value is the probability that t, 27 degrees of freedom, is less than negative 0.949. So when we do that, we need to do our t.dist, and we need to do our negative 0.949, and our degrees of freedom is 27, and it is true. So we end up finding out that we get 0.175. So if our p-value is 0.175, if we wanted to test it against an alpha of 0.01 or even 0.05, we're not going to find something statistically significant because this is 0.175. That's 17.5%. We're trying to compare it to 1% and 5%, which are our most common alpha values. And neither one of those is smaller than the p-value that we got. Right? So what I'm going to do for this one is typically if I don't ask you, or not ask you, but I don't tell you what alpha is, you generally are going to assume that it's 95%. And this one, I think I just failed to say it should be a 99% because I'd rather do a 99% on this one. We do a lot of 95s, so I'd like to do a 99 on this one. So we're just going to say if we let alpha right? Let alpha equal 0.01. And then we'll say then our p-value is larger than alpha, so therefore we would fail to reject our null, which means we don't have enough evidence to show that the new treatment is actually better. So that's what we're going to say. We would say there is not enough evidence, right? There's not enough evidence to show that on average, right? On average, the new treatment, there we go, the new treatment is better than the standard treatment. I wish I could write as fast as I speak. The standard treatment. There we go. So therefore, our results are not statistically significant, which means we would fail to reject the null hypothesis, right? So that all fits together. Now, could we confirm this with a 99% confidence interval? Absolutely, which is what we're going to do. So if we're going to confirm here, let's scroll up a little bit. Let's go ahead and confirm with a 99% confidence interval. And remember, because our confidence interval is an interval estimate for what the true difference in the means is, if zero is in our interval, that means it's a reasonable value for the true difference in the population means. So if zero is in our confidence interval, we have to fail to reject. So let's see what happens. And this is where things get kind of fun, because if you look back up at our test, what did we say? We said that our alternative is that mu A is less than mu B, or mu A minus mu B is less than 0. That is a left-sided confidence interval, right? This is a left-hand test. This is a left-hand sided confidence interval. So we're only going to have a single-sided confidence interval. So this is a left confidence interval, which means it's going to start at negative infinity, and we're not going to have an alpha over 2. We're just going to have to use alpha because we want all of that probability in the one tail. There are not two, there's just one. So let's find it. Our 99% confidence interval then is going to go from negative infinity up to our sample statistic x bar minus y bar, not minus but plus our t sub alpha comma nu. And it has to be alpha because it is all of our probability. And then times our standard error, which is just going to be the standard deviation of the sample from population A over its size plus squared, the sample standard deviation squared. And then again, the variance of population B, our sample from population B, over its size, M. So let's see what this looks like. So we end up with a negative infinity, comma. We know that x bar minus y bar is a negative 3.73. We have to add to that our t sub alpha nu. So that's t sub alpha is 0.01, and nu was 27. And then we have our square root of 11.4 squared over 15 plus 10.09 squared over 15. And what we need to do is figure out what t sub alpha comma nu is. Well, remember we're going to do a t dot dist, right? Or t inverse. You have to figure out what it is you need. And when we find it, we talked about it so much I want you to try it on your own. So we end up with a negative infinity, and it's going to go to negative 3.73 plus, and hopefully what you found for t sub 0.01 comma 27. So area of 0.01 under our curve and degrees of freedom of 27. Hopefully you found 2.473. And hopefully you use t dot inverse for that one, right? T dot inv. And that would be times our square roots of all of this. So our 11.4 squared over 15 plus our 10.09 squared over 15. And when we do all of this together, we come up with a 99% confidence interval that goes from negative infinity up to 5.99. We would say since 0 is in the interval, we know that 0 is plausible for the actual mean of the differences of the means in the populations. So since 0 is in our interval, then we would fail to reject the null, right? So this confirms our hypothesis test. And our results are not statistically significant. For example, 9.3.2, we're going to talk about an unpaired two-sample problem, and our experimenter observes n equals 14 data points with an x bar of 32.45 and a standard deviation of 4.3 from population A, and m is equal to 14 data points, and y bar equals 41.45, and standard deviation of y is 5.23, all from population B. So this one doesn't have a big setup, doesn't tell you what the context of the problem is or anything. Just says, here's the data that you need, here's all the information you need, now let's do something with it. So pretty straightforward. So we wanted to construct a 99% two-sided confidence interval for mu A minus mu B. How could we do that? Well, we're talking two-sided, so we'll bear that in mind. So our 99% confidence interval here will equal x bar minus y bar plus or minus t sub alpha over 2 comma nu times our square root of s sub x squared over n plus s sub y squared over m. Same thing as before, but now it's two-sided. So let's talk about, first of all, our degrees of freedom. We can't do anything without knowing what those are. So let's see here. We'll take a little sidebar here to find our degrees of freedom. And so we'll end up, let's see here, with 4.30 squared over 14, plus our 5.23 squared over 14 as well. And the whole thing is squared. And then we're going to divide it by, and it's going to look somewhat similar, 4.30 to the fourth now over 14 squared times 14 minus 1 plus 5.23 to the fourth over 14 squared times 14 minus 1. And when we calculate all of this, we end up with 25.06, which means we round down to 25. The other thing we need to know is what t sub alpha over 2 comma nu is here. That would be t sub 0.01 over 2 comma our 25, or t sub 0.005 comma 25. And when we do that, we end up with 2.7874. And now we just have to plug stuff in. So let's see what happens when we just start plugging things in. So our confidence interval will be x bar minus y bar. So x bar is 32.45 minus y bar, which is 41.45. And we're going to say plus or minus our 2.7874, right? Our t sub alpha over 2 nu, which again, this is t inverse, times our square rooty root here of all this stuff. So square root of 4.30 squared over 14 plus 5.23 squared over 14. And when we put all of this work together, we find out that our 99% confidence interval is negative 14.0440 up to negative 3.9560. And there's our 99% confidence interval. So when you are given a problem and you can take away from it x bar, y bar, the size of sample A, the size of sample B, and their standard deviations, that's really all you need. If we're doing a hypothesis test, you also have to know whether we want our alternative to be not equal, greater, or less. Right? So part B says then, let's try to relate it back. Let's see what happens. Part B says, well, first of all, is 0 in this interval? The answer is no, which means it's not a plausible value, so we would reject our null. So let's see what those null and our alternative hypotheses look like, but they're always going to relate to 0. I mean, I say always, but it's probably like 99.9% of the time. So let's see what we've got. B says consider the two-sided hypothesis test for null being that mu A is equal to mu B. Now, two-sided implies then that our alternative is that they are not equal. So does the significance level alpha equals 0.01 test reject or fail to reject the null hypothesis? Well, let's find out. So our null is that mu A equals mu B, or mu A minus mu B is equal to 0. And our alternative then would be that mu A does not equal mu B, or that mu A minus mu B, it does not equal 0. That's how we get our two-sided test. Has to be not equal. So let's find our test statistic. Okay, so here's our test statistic. And that means that we are using a t this time. So we have our t, which is going to be 32.45 minus 41.45 minus our null hypothesized value of 0 over our square root of 4.3 squared over 14 plus 5.23 squared over 14. And we end up with a t-test statistic of negative 4.9736. Well, we have to then turn around and find our p-value. So our p-value is going to equal 2 times our probability that x is less than negative 4.9736. And this is where we do our t.dist, and this is where t.dist.2t comes in awfully handy. So we end up with 2 times all of this gets us a 3.9906 times 10 to the negative fifth, or approximately 0.00004, which is approximately 0. And since our p-value is definitely then less than alpha, because 0.00004 or approximately 0 is less than 0.01, therefore we would reject the null. For our last example, 9.3.3, we said a random sample of n equals 16 1 kilogram sugar packets of brand A have weights with a sample mean of x bar equals 1.053 kilograms and a sample standard deviation S sub x of 0.058 kilograms. In addition, a random sample of m equals 16 1 kilogram sugar packets of brand B have weights with a sample mean y bar equals 1.071 kilograms and a sample standard deviation S sub y of 0.062 kilograms. Is it safe to conclude that brand B sugar packets weigh slightly more on average than brand A sugar packets? So this time, we're going to state our hypotheses just a little differently because all of the other examples have had negatives. So let's see if we can maybe see what it looks like to work with a positive. It's not all that different, but we'll work with it. So let's first of all write out what we've got. N equals 16. X bar is 1.053 kilograms. And S sub x is 0.058 kilograms. We also have that M is 16. Y bar is 1.071. And S sub y is 0.062. And these guys are kilograms. What if we set in our null and our alternative something slightly different than what we did before? Because the question asks, is it safe to conclude that brand B sugar packets weigh slightly more? So that would mean that B minus A on average should be positive. So what if we did mu B is greater than mu A? And our null then would be that mu B is less than or equal to mu A. What does that make our sample statistic? Our sample statistic is the measurement we're making. If we're starting with mu B, that means that's y bar, and we're subtracting x bar. So we get 1.071 minus 1.053, or y bar minus x bar equals 0.018. So we have our sample statistic, but we don't have our degrees of freedom yet. So we better do that. Yes, with that long formula. Yes, you'll be okay. You'll make it. And yes, you have to do it on the next exam, potentially. So before all those questions start coming up, I'll go ahead and head them off with a pass there. So we have 0.058 squared over 16 plus 0.062 squared over 16, and we'll square the whole thing. And in our denominator, we have 0.058 to the fourth over 16 squared times 16 minus 1 plus 0.062 to the fourth over 16 squared times 16 minus 1. And we end up with a grand total of 29.87, which means we round down to 29. Where do we go next? Well, now we know our degrees of freedom, we know our sample statistics, so now let's find our test statistic. So we're going to find our test statistic. So in this case, T then is this difference, right? 1.053 minus 1. Oops, sorry, put them in the wrong order. 1.071 minus 1.053 minus 0 all over the square root of 0.058 squared over 16 plus 0.062 squared all over 16. Or we get a t-value of approximately 0.848. Well, considering we were going for B being greater than A, which means B minus A is positive, I think we're on the right track. So let's find our p-value. So our p-value here is going to equal the probability, and our results are at least 0.848. Well, I think it's 8.481 maybe, but it's okay. We'll leave it at 0.848. So this is where we'd use our t dot dist, I think it's dot right tail, and we'd have our 0.848 with our degrees of freedom of 29. So we end up with a p-value of 0.2017. And if we assume alpha of 0.05, because if I ever forget to give it to you, just assume it's 5%. It's 0.05. So we would say since, oops, let's see here, there we go. Since our p-value is greater than alpha, we would fail to reject the null. There is not sufficient evidence there's not sufficient evidence to show that on average brand B sugar packets weigh more than brand A sugar packets. Brand A sugar packets. And that is this section. So make sure you do the assignment that I sent home with you after the exam and bring it back on Monday. Have a great weekend, everyone.